So we're going to keep seeing this slide and slight modifications of it. This covers all of our core aspects that we want for nomenclature. You really need to make sure you've got this kind of nailed down and unlocked, because this is what you really need to be able to get through nomenclature. There are tons more rules than this, so don't even get me started on that, but focus on this part. After that, let's see if I can get my computer moving. We want to be able to identify our main chain. Okay, and this, we've got a variety of different examples to kind of pop in here to make it a little bit more challenging. One of the notes in this says that we also have to include the highest priority functional group. All of these are alkanes, so we don't have a functional group to worry about, so we just have to find our longest carbon chain. So what I'm going to go through and do is do what I would recommend you do, which is identify that longest carbon chain just by circling it. Okay? So if we pick out our drawing, we would circle through here. We've got 1, 2, 3, 4 carbons. 4 carbons. 4 carbons. And now we have some potential challenges, okay? Because the bottom left branches and the bottom right introduces a cyclic structure. So go ahead and pause the video and take a swing at it and see what you can come up with. And now that we're back, we can try and go through and identify this. And so the way that I would actually go through and do for the lower left is start actually numbering and then start picking other numbering options. So 1, 2, 3, 4, 5, 6, 7 in red. Let's try purple. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so purple is now better than the red counting system that I went through and did, because I got to 8. We tried blue. 1, 2, 3, 4, 5. Let's go the other branch. 6, 7. Doesn't work, so purple is still winning at 8. And then let's go through and try an orange, because there was a different point. We go 1, 2, 3, 4, 5, 6, 7, 8, 9. So there we go. We've got 9 carbons being our largest amount. Our main chain, once it's been identified, I would again recommend circling it, because you probably aren't using colors. Once you've got that, the next step would be identifying your substituents. And so this is where separately circling those can help you to identify and separate those away. So we're looking at 9 carbons there. Note that one of the things that makes this kind of question challenging is that our longest carbon chain isn't read left to right like it was with the top ones, or in a straight line. It kind of goes on that diagonal. Similar to kind of crosswords, our main chain can go every which direction. It could even circle back on itself. So you got to be a little bit careful with that. When we move to the lower right, we've got a cyclic structure. Cyclic structures can be considered the longest chain. So what we should do is identify that cyclic structure first. 1, 2, 3, 4, 5. There's 5 carbons in that cyclic. I do not go 1, 2, 3, 4, 5 and then count out to 6, because that 6th isn't in the cyclic structure. And if I were to name my longest carbon chain according to the cyclo rules, it wouldn't make sense, because cyclohex isn't true. There's only 5 carbons in that main chain. The next thing I could do is look at what's happening outside. 1, 2, 3. We're looking at 3 carbons for those people saying, but what about the 4th? Well, that 4th one is a substituent on that blue 3 carbon chain. Okay, so that wouldn't count as part of the longest continuous chain. It's not counting all the carbons, continuous chain. So in this respect, we're looking at the 5 being our main chain. That's going to drive the name for this. That will now be a cyclopentane. Okay, so the idea was to give a little bit of practice with identifying that. Some of the things you do need to watch out is those sigma bond rotations. For instance, those top 2 on the, or in fact all top 3, are representing the exact same compound, but they look different. And really the difference between these 2 is all we did was rotate around this sigma bond. As we rotate that bond, this bond now changes space, and really all we're looking at is the exact same compound. Okay, so sigma rotations can make a structure look different when it isn't. So you have to be very careful with those sigma bond rotations. One of the things that can help you go through to identify whether it was just a sigma bond rotation is naming. Because if you name each of those, they're both going to be the same name, butane, which means they are the same compound. Okay. Rings define their own chain. They are not part of a chain, which was the lower right-hand kind of corner. Okay, the big thing that we really wanted to get out of this was this whole sigma rotation thing with those top two, because it's now going to address this kind of differential between what makes a compound unique from another compound. Those top two are identical. We see that with the same name. Therefore, we need to be able to explain the difference between those. Okay, and we'll see that in a second. I forgot that I've got this little demonstration first. Each of these names has something wrong with it. So you should be able to go through and figure out why it is wrong and figure out how you would fix it. One of the problems on this why it's wrong is it's not obvious by just looking at the name, particularly if we look at the color coding box all the way up at the top, because that color coding box actually breaks down each of the aspects of the name and how you would put it together. Some parts are shown always, some parts aren't. We just have to kind of work through it. So let's take a look at the, we'll take a look at the first one on the left, okay? How I would break this down is to start in with the number of carbons, okay, in our root structure. So we're looking at a hex, okay? I don't see that shape acronym coming out of it, and that shape would be a cyclo. So I'm gonna go straight chain. So 2, 4, 6, okay? Note that I do those all as sigma bonds, and that's added to the fact that we have that aim, which is really telling us that within that main chain, those are all sp3 carbons. So no double bonds, no triple bonds. Okay. The E part of the name is just the ending on the name, so we don't really care about that. Okay. The next part, we have some methyls. A methyl would just be a CH3, a single carbon. So the question then is, where is that CH3 located? Okay. So its locator is found in front, 3. I can number my main chain, my green structure, 1, 2, 3, 4, 5, 6, or I could number it 1, 2, 3, 4, 5, 6. Either way I number it doesn't matter, right, as long as I'm consistent. With one slight caveat. Realize that when we're looking at nomenclature, it's going to be multiple choice. There are so many different ways that you could screw up writing a name that it is insanely tedious to assign points for naming. It either is all or nothing, which means we might as well just go multiple choice. Okay? So if we're being asked to identify the structure, very rarely will you see the structure match the exact same format as you would read. What do I mean? We read left to right, top to bottom. So if you number your structure 1, 2, 3, 4, 5, 6 as in black, left to right, you're matching the instinctive reading nature. Right? Why is that a big deal? Well, if that's what you're matching, the odds of seeing that as a multiple choice and being correct are slim to none. The reason being, you could accidentally get the answer right. And we don't want accidental correct answers. We want absolute correct answers. So very often, if you look at a multiple choice test on nomenclature, you will see your main chain numbered right to left, or up to down, or down to up. I drew those arrows wrong, but you will see it kind of mishmashed off of that left to right straight line axis. Okay? Because what we're trying to do is ensure that you actually know the name and you aren't lucking into an answer. So be aware of that. So if you're trying to draw the structure, it probably makes sense to not use the black numbering, because that black numbering probably isn't going to match one of your answer choices. Okay? You could try and spin it off axis. There's so many different ways you could spin off axis, though, that it really just makes sense just to start numbering right to left, because you're going to increase the odds of immediately finding the answer. Okay, so if we do that numbering, third position would be here. I want my CH3. Okay. The careful observer will note that we have a di in front of that methyl, and this is really an amount. How many times does that methyl show up? Okay, well, it says dimethyl, which means I need two methyls. There needs to be a second methyl in this structure. Well, the number location has to be specified for every single substituent. So I have two methyls. Where do the two methyls go? I only have one locator mentioned here. Okay, so we could probably assume that the author meant we wanted the CH3 at the 3 position because we didn't specify another locator. That is technically an assumption, and it should not be done. So the error in this question is that it should be 3,3-dimethyl hexane. Okay? Now we have the correct structure. Now we could try and look for this in our multiple choice. In this case, it's why it's wrong. We would go through and explain that the locator wasn't correctly specified. Okay? You should be able to go through and do the remaining two. Yeah, so go ahead and pause and see what you can come up with. And now that you've come up with them, we can go through and look at these relatively quickly. We have that hex again. Before I immediately jump on the just drawing a straight chain, I do have that cyclo. I know it's kind of faint to see, but I ran out of colors. So we're looking at a cyclohexane. Again, the hybridization being ane means that we are looking at all single bonds, so we're good there. We then go through with our methyls. On a ring, I can number wherever I want. And I'm going to start doing 1, 2, 3, 4, 5, 6. Methyl, I need to attach the methyl to my ring. Where should I attach it? This says to attach it at the 3 position. Okay, so I could put it 3. We again have that di issue. Again, we can make the assumption that we could put the methyl there. So we do again encounter that same issue. This should be located as 3,3-dimethyl. Okay, that seems awfully suspicious because that's the exact same issue we had in the previous case. This name is even further wrong. As soon as we have a cyclo structure, our substituent needs to be located, our first substituent, our highest priority one, needs to be located at position 1. We always want to use the smallest possible numbers. Okay? 1 is smaller than 3, which means the name should actually be 1,1-dimethyl cyclo la 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 la. Okay? Because they're ones, sometimes you won't see people specify those. If you're running IUPAC, you should specify them. Okay? We'll clear all that away. Take a look at the last one. Last one, we're looking at a hex structure again. Note no cyclo. So 2, 4, 6. Okay. We're still ane, so sp3 hybridized all the way through. But here we have a different ending in all. That all means we have an alcohol. Again, I'm going to number the opposite direction. So there's my alcohol. 1, 2, 3, 4, 5, 6. At the 3 position, I want methyls, or I want a methyl. It says di, so I should put in a second one. Okay, and this should be 3,3-dimethyl hexane 2-all. Okay, so again, we run into the same issue. We should have specified that locator for where that 3 position was. So again, kind of a boring one because we again goofed on that numbering. Okay, incredibly easy to make these mistakes. It really requires practice and just looking at a whole bunch of them. Okay, don't stress a whole lot if you're missing out on spaces or hyphens or even spelling errors, because again, multiple choice when it comes to the exams. We want to go back and look at that butane kind of quickly. So if we were to draw out our butane, that's 4 carbons. We drew one out where it was this. We could have done a sigma bond rotation. We could have done that. We also could have done this. So that S, when we're talking about butanes, says nothing about this being necessarily a straight chain. So if you see reference to hexanes, right, or octanes, as you might see at the gas station, it's really just saying you've got compounds that have that many carbons in it. The exact order in which those atoms are connected isn't specified. Okay? Why does this become important to us? Well, these two are identical. Okay? They're the exact same compound, just a sigma rotation. So we've just kind of shifted our view, if you will. If we take a look at that last one, it is also 4 carbons. It is also 10 hydrogens. There would be our 9, and then remember the implied hydrogen in the middle. But it can't be identical. Even though it has the same formula, it definitely is going to have different intermolecular forces because, for instance, we can't do that sigma bond rotation to actually make the structure look different, right? So we need some way to classify that butane as different from the other butanes. One thing that you might see pop up is you'll see reference for these two being called N-butane. Okay? That's really just saying it's straight chain. Okay, so an N-butane is a straight chain. So how do we address what's going on with this one? Well, we could go through and name it. 1, 2, 3. It's a propane, and it's going to be a methyl at the 2 position, 2-methyl propane. But didn't we say it was a butane? Again, the butanes with that S is really just saying 4 carbons. Okay, so it's that plural. So the name allows us to see that it's different, but is it different? It has the same formula. So now we run into this kind of issue with how we classify things as being distinct from each other. Okay? That classification, when applied to people, is usually a bad thing. When it comes to chemistry, what we're trying to do is be able to organize a flowchart of how those systems are related. Okay? So these two compounds are related to each other, but they're not identical. Okay? So how do we go through and do this? This is where we introduce some kind of terminology. Different is going to specifically refer to the molecular formulas. Your molecular formulas are different. Identical, the formulas are the same and the structures are superimposable. Okay? So the case for that would be now these two red structures. Okay? We have the same formulas and our structures are superimposable. For the gifted eye, though, you might say, how is this superimpose? Don't they aim the opposite direction? Again, we have to recognize that sigma bond rotation. We're allowed to rotate sigma bonds to get to the superimposability. Okay? And that is challenging to manipulate, and it takes practice to deal with, usually with a model kit. Okay? The last kind of category we're going to drop in there is isomers. Okay? The molecular formulas are the same, and the structures are not superimposable. So if we were going to look at this one is different from the others because it has 5 carbons. 4, 4, and 4. These two are identical because with a sigma bond rotation, they superimpose, and then these two are now isomers of each other, okay? Because they have the same formula, but they're not superimposable. There's nothing I can do to rotate them, okay? The way that I think about those kind of isomers is if you have to break a bond to make them superimposable, then they're isomers, okay? And that breaking bond is going to become more relevant as we continue through, okay? And really the best way to do this is to look at kind of a flow chart. So take two molecules, in this case A and B, and ask yourself, do they have the same formula? If they have different formulas, well, then they're different. If they have the same formula, then you have to ask, are they superimposable? That superimposable gets tricky because remember sigma bond rotations. If they are superimposable, then yes, those two compounds are identical. If no, then they're isomers. Isomers can be further subcategorized by looking at atom connectivity. Okay, do they have the same connectivity of the atoms? If no, they're structural isomers or constitutional isomers. If yes, they're now stereoisomers. Okay? So really what you're just trying to do is to organize the relationship between each of these pieces by moving through the flowchart. Okay? Because our exams are by definition open note, because I can't really control your access to notes, you should probably have this flowchart handy when moving through the exams. Okay? And before you start printing out this one, realize there's another one that's a little bit more complicated that we're probably also going to see in this first exam. Okay? So it's just a way to classify our compounds. Sometimes nomenclature can help out with this, sometimes not. It largely depends kind of where you're more comfortable. This is starting to move into the three-dimensional and spatial representations. If you look at our drawings, they do not look three-dimensional. They represent three-dimensional things. You have to know that connection. Okay? So start pulling out the model kits and playing with them. If we were to go through and take a look at this as a quick example, the relationship between these structures, you should hopefully be able to quickly identify that this one has an extra carbon and therefore they are different, okay? Which was really a typo because that extra carbon shouldn't have been there, so let's fix it. And now say, what is the relationship between those structures? Well, they're going to have the same formulas. You don't have to draw out the formula to figure it out. Look at the shapes. The shapes match all the way across. Okay? So they have the same formulas. Are they superimposable? Okay? Well, wedges meant they were coming out at you, so yep, that wedge would superimpose. The other position is a wedge versus a dash. The wedge is coming at you, the dash is going away. So those don't superimpose. If you built these models and tried to flip and move them around, what you will find is that you can't superimpose them. There's no way that you could possibly get these two to overlap, which means they're non-superimposable, which then makes them isomers, which moves us to the next question, atom connectivity. Right? Do they have the same atom connectivity? Well, to answer that question, let's number 1, 2, 3, 4, 5, 6. And in the bottom case, we're going to number similarly 1, 2, 3, 4, 5, 6. At position 1 in the red one, do I have a methyl? Yes. Do I have a methyl in the green one? Yes. Position 2, do I have a methyl? Yes. And yes. Same atom connectivity. Because they have the same atom connectivity, they are now stereoisomers. Okay? If that atom connectivity was different, say we took the methyl and put it over here, now they would be structural isomers. Okay? Takes a little bit of practice of getting used to and manipulating. You will see an activity that I'm not sure where it's actually going to fall. I think it's going to have to fall in lab that looks at models and trying to get you to think through these spatial relationships. Okay? With that, I won't worry about that. Actually, I will worry about that. Similar to our double bonds, rings have a similar feature. These two methyls are on the same side because they're both up. So these would be cis. These would be trans. Okay? You will be seeing a video about E and Z with respect to cis and trans. E and Z applies only to double bonds. Cis and trans applies to anything. Okay? Any two groups, are they on the same side or opposite side of whatever your locator is? In the case of rings, it's same side of the ring. Okay? With that, I think we are now actually done. Yep. So thanks for watching. I hope that made sense. Let me know if you've got any questions. Have a good day.